You know what's strange? It's not that we don't understand the universe. It's that we think we understand parts of it well enough to stop asking questions. And that quiet confidence is usually where things begin to fall apart. Because once you decide something is simple, you stop looking closely. And when you stop looking closely, you stop noticing the details that don't quite fit, the ones that sit there quietly for years, waiting for the right instrument to expose them. And that's exactly what happened when the James Webb Space Telescope was pointed in a direction it was never really meant to look. This telescope wasn't built for nearby worlds, not for planets we've known since the early days of astronomy, not for something sitting comfortably within our own solar system, but for the deep past, for the faint glow of galaxies forming billions of years ago, for atmospheres of distant exoplanets whose light has traveled across space longer than human civilization has existed. Everything about it was designed to stretch our vision outward, to push beyond what we can see, not to revisit something we thought we already understood. And yet, in January 2025, instead of staring into the ancient universe, it turned its attention toward Uranus, a world that, for most people, barely feels like a mystery at all. Now I want you to think about Uranus the way people usually do. Not as a scientific object, but as an idea. It's the quiet one, the distant blue sphere tilted awkwardly on its side. A planet that doesn't compete for attention, doesn't erupt with violent storms like Jupiter, or display the elegance of Saturn's rings. A world that has been sitting there almost unchanged in our imagination. Since we first began mapping the solar system, it's the kind of place you assume has already given up its secrets, or at least the kind of place where nothing truly surprising is left to find. And that assumption, that subtle sense of familiarity, is exactly what makes what came next so unsettling. Because Webb didn't just take a quick look and move on. It didn't capture a single image and add it to a catalog. It watched carefully, continuously, for 15 hours straight, tracking the planet as it rotated, collecting data point by point, layer by layer, not just from the visible clouds, but from something far less obvious, something that exists above them like an invisible shell. It focused on the ionosphere, the region where a planet's atmosphere stops behaving like ordinary gas and starts interacting with space itself, where sunlight and charged particles tear electrons away from atoms and create a strange, electrically active layer that most people never think about. And until now, no one had ever truly mapped on Uranus. For decades, everything we knew about that region came from fragments, a brief encounter by Voyager 2 inches 1,986, and a handful of indirect measurements made from Earth. Incomplete, distorted, like trying to understand a landscape through a fogged window. We had models, of course, carefully built frameworks that described how the ionosphere should behave, how temperature should vary with altitude, how charged particles should distribute themselves under the influence of sunlight and magnetic fields. And those models weren't guesses. They were based on physics we trust, on patterns observed across other planets, on decades of accumulated understanding. And then Webb came along and quietly showed us that those expectations might be wrong. Not dramatically wrong in a way that announces itself with explosions or obvious contradictions, but wrong in a quieter, more unsettling way, where the data doesn't line up, where patterns appear that shouldn't be there, where temperatures and structures refuse to follow the rules we thought we understood. It's the kind of discrepancy that doesn't immediately give you answers. It gives you questions. And worse than that, it makes you realize that the questions you've been asking might not even be the right ones. And this is where the story shifts from being about a telescope or a planet to something more uncomfortable. Because what Webb revealed wasn't just a new detail about Uranus. It exposed a gap in our understanding that had been sitting there unnoticed, hidden behind our assumptions. We pointed one of the most advanced instruments ever built at a world we thought was simple. And instead of confirming what we believed, it showed us that even here, even in our own solar system, there are processes we don't fully grasp, patterns we can't yet explain, and histories we haven't correctly reconstructed. So when I say the telescope looked the wrong way, I don't mean it made a mistake. I mean it broke a habit. It ignored our expectations about where discoveries are supposed to come from. And in doing so, it revealed something far more interesting than distant galaxies ever could in that moment. It reminded us that the unknown isn't always far away. Sometimes it's been sitting right in front of us the entire time, waiting for us to finally look at it properly. Now here's where things start to get uncomfortable in a very specific way. Not because Uranus is mysterious, but because it is the wrong kind of mysterious, the kind that doesn't just add new details to what we already know, but quietly undermines the structure we thought was holding everything together. Because if you really want to understand why the observations from the James Webb Space Telescope matter, you have to look at something most people never think about when they picture a planet. Something invisible. Something you cannot see even if you were standing right next to it. And that is its magnetic field. Every planet, at least the major ones, has a magnetic field. And we like to imagine these fields as neat and orderly, like Earth's, where the magnetic axis lines up more or less with the planet's rotation, giving us something intuitive, something stable, something that makes sense when you hold a compass in your hand and watch it point north. Even when things get extreme, like with Jupiter, the field is still structured, still centered, still behaving in a way that follows patterns we can model and predict. But then you get to Uranus, and suddenly that entire sense of order collapses. Because Uranus doesn't just have a tilted magnetic field. It has one that seems almost misplaced, like it doesn't quite belong to the planet it's attached to. The magnetic axis is tilted by nearly 60 degrees relative to the planet's rotation, which is already strange enough, but it gets worse, because the field itself is not centered. It is offset, pushed significantly away from the planet's core, as if the internal dynamo that generates it is somehow displaced or distorted. And you have to remember, this is happening on a planet that is already tilted 98 degrees on its side, rolling through space in a way that defies the neat orbital geometry we see elsewhere in the solar system. When you combine those two facts, the result is not just unusual, it is chaotic. A magnetic field that doesn't simply spin, but wobbles, sweeps, and twists through space as the planet rotates. Now I want you to pause and think about what that actually means. Because a magnetic field is not just some abstract property. It shapes how a planet interacts with the solar wind, how charged particles move around it, how energy is distributed through its upper atmosphere. It defines the environment above the planet just as much as gravity defines the surface below. So when the magnetic field behaves strangely, everything built on top of it begins to behave strangely as well. And sitting right at the boundary between that distorted magnetic field and the upper reaches of the atmosphere is the ionosphere, the region that Webb was observing. If the magnetic field is the skeleton of a planet's interaction with space, then the ionosphere is its skin, a thin, dynamic layer where sunlight and high-energy particles strip electrons from atoms. creating a mixture of ions and free electrons that responds directly to electromagnetic forces. On Earth, this layer reflects radio waves and supports communication systems. On Jupiter, it powers massive auroras. But on Uranus, until very recently, it was almost entirely unknown. Not because it wasn't important, but because we simply didn't have the tools to see it clearly. And this is where the story becomes more than just a description of something strange. Because when Webb began mapping this region, it wasn't just observing an atmosphere. It was observing the interaction between a broken magnetic field and a layer of charged particles that should, in theory, organize themselves according to that field. But instead of finding something that fits neatly into our expectations, the data revealed structures that don't align cleanly with the models, vertical variations that don't behave the way they should, and patterns that suggest the system is more complex than we assume. The problem here is subtle, and that's what makes it so important. If the magnetic field were simply chaotic, then randomness would be the explanation, but what Webb is hinting at is something more interesting. A system that is not random, but not fully understood either. A system where there is structure, but the rules that generate that structure are not the ones we thought we were applying. It's like looking at a pattern that clearly has order, but not recognizing the language it's written in. So what you end up with is a layered mystery, a planet whose magnetic field doesn't behave the way planetary magnetic fields are supposed to behave, and an ionosphere that responds to that field in ways that don't match our predictions, creating a feedback between structure and behavior that we can observe, but not yet fully explain. And this is exactly why the observations matter, because they don't just give us more data about Uranus. They force us to confront the possibility that the frameworks we use to understand planetary environments might be incomplete, especially when applied to worlds that don't follow the rules we derive from Earth and its more orderly neighbors. And once you see it that way, Uranus stops being the quiet, forgettable planet sitting at the edge of the solar system, and becomes something far more interesting. A natural experiment in how far the laws we think we understand can be stretched before they start to break, or more precisely, before we realize that it's not the laws that are breaking. It's our interpretation of them that was never quite right to begin with. Now here's the part where everything shifts from speculation to something far more concrete. And I want you to pay close attention, because this is not just about a better observation. It's about a completely different way of seeing. Up until this point, everything we thought we knew about Uranus was built on fragments, brief encounters, indirect measurements, and models carefully stitched together from incomplete data, like trying to reconstruct an entire landscape from a handful of photographs taken in bad weather. And then, on January 19th, downtown Arjou, the James Webb Space Telescope did something deceptively simple that changed the nature of the problem entirely. It watched, not for a few minutes, not for a quick snapshot, but for 15 continuous hours, tracking the planet as it rotated, collecting data in a way that no instrument had ever done before. And that distinction matters more than it might seem at first, because when you observe something continuously over time, you stop seeing isolated points and start seeing relationships, patterns that only emerge when you follow a system as it evolves. Uranus rotates slowly, taking about 17 hours to complete a full turn, which means that in those 15 hours, Webb was able to observe nearly an entire rotation, capturing information from almost every longitude, effectively building a global view from a single uninterrupted session. But it wasn't just the duration that made this observation unique. It was the way the data was collected. Webb used an instrument called NIRSpec, a near-infrared spectrograph that doesn't simply take images, but breaks light apart into its component wavelengths across a two-dimensional field, meaning that for every point across the face of the planet, it can measure how that light varies with wavelength. And from that, infer properties like temperature, density, and chemical composition at different altitudes. So instead of getting a flat picture, what scientists obtained was something far richer: a layered structure, a vertical profile of the ionosphere, built point by point across the entire visible disk of the planet. Now I want you to stop and think about what that actually means, because this is the first time we've had something like this for Uranus. Before Webb, the best data we had came from Voyager 2 inches, 1,986, which flew past the planet once, collecting data over a matter of hours, and from ground-based telescopes that had to peer through Earth's own atmosphere, limiting what they could resolve. Those observations were valuable, of course, but they were incomplete. Like looking at a sculpture through a narrow slit and trying to imagine its full shape. What Webb did was remove that limitation, giving us a continuous, multidimensional view that allowed scientists to trace how the ionosphere changes, not just across the planet, but vertically, layer by layer. And what they found was not just more detail, but a kind of structure that had never been seen before. The ionosphere of Uranus is not uniform, not a smooth gradient that changes predictably with altitude, but something far more complex, with regions where temperature peaks not at the top, as you might expect, but somewhere in the middle, thousands of kilometers above the cloud tops, and with variations that suggest energy is being distributed in ways we don't fully understand. The average temperature measured was around 426 Kelvin, which might sound high until you realize that it is significantly lower than what previous models and observations had predicted, extending a cooling trend that has been quietly unfolding for decades. But beyond the numbers, what makes this observation so important is the coherence of the data set itself. This is not a patchwork of measurements taken under different conditions at different times. It is a single, continuous record, capturing the state of the ionosphere as the planet rotates, allowing scientists to distinguish between local variations and global patterns, between noise and structure. It is, in a very real sense, the closest thing we have to a complete snapshot of Uranus's upper atmosphere. And yet, instead of resolving the mysteries, it has made them sharper. Because when you finally see something clearly, you don't just confirm what you thought you knew. You also expose everything that doesn't fit, every discrepancy, every deviation from expectation. And that is exactly what happened here. The vertical separation between temperature peaks and ion density peaks, the lower than expected densities, the overall cooling trend, all of these features point toward processes that are either missing from our models or not fully understood, suggesting that energy is moving through the system in ways we haven't accounted for, possibly influenced by the chaotic magnetic field, the solar wind, or internal dynamics deeper within the planet. So what Webb's 15-hour watch has given us is not just a better map, but a new kind of problem, one that is more precise, more constrained, and therefore harder to ignore, We are no longer dealing with a blurry picture where anything could be explained away by uncertainty. We are dealing with a detailed structure that demands an explanation, and that changes the nature of the conversation entirely. Because now, when the data doesn't match the models, we can't just say we need better observations. We already have them. The question now is whether we are ready to rethink the assumptions that those models were built on in the first place. Now, here is the part that should really bother you. Not in an obvious, dramatic way, but in that quiet, persistent way where something doesn't quite fit and you can't ignore it anymore. Because once you see it clearly, it starts to reshape how you think about everything that came before. We're not talking about a sudden explosion, not a violent storm, not some spectacular event that announces itself across the solar system, but something far more subtle, and in many ways far more unsettling. Uranus has been cooling steadily, measurably, for over 3 decades, and we don't fully understand why. Now, at first glance, that might not sound surprising, because Uranus is already an incredibly cold world, orbiting nearly 3 billion kilometers from the sun, receiving only a tiny fraction of the sunlight that warms Earth. So you might think, of course it's cold. Of course it's losing heat. What else would it do? But that intuition is exactly where the problem begins. Because when you look more carefully, the numbers don't behave the way that simple picture would suggest. The upper atmosphere, particularly the ionosphere that the James Webb Space Telescope has now mapped in unprecedented detail, is not just cold. It is colder than expected. And more importantly, it has been getting colder in a consistent trend that stretches back to the early 1990s. And that consistency is what makes this so difficult to dismiss. Because random fluctuations are easy to explain away. They come and go. They average out. But a long-term trend, a gradual decline in temperature sustained over 30 years, implies that something fundamental has changed, either in how energy is entering the system, how it is being stored, or how it is being lost to space. The average temperature measured by Webb, around 426 Kelvin, may not sound extreme, but it is significantly lower than earlier measurements and models predicted, reinforcing the idea that this is not a short-term anomaly, but part of an ongoing process. So the question becomes unavoidable, and I want you to really sit with this for a moment. Where was the heat coming from in the first place? And why is it disappearing now? Because for a planet like Uranus, the balance of energy is already unusual, unlike Jupiter or Saturn, which radiate large amounts of internal heat left over from their formation. Uranus appears almost quiet by comparison, emitting only slightly more energy than it receives from the sun, roughly about 12% more, which suggests that while it is not completely inactive internally, whatever heat source it has is weak, subtle, almost like a whisper compared to the roar of the gas giants. For decades, scientists even suspected that Uranus might be essentially dead inside, its internal heat somehow trapped or depleted, possibly the result of a catastrophic event in its past that disrupted its structure and left it tilted on its side. But more recent studies have challenged that idea, showing that the planet is not entirely inert, that there is still some internal energy leaking outward, which makes the cooling of the upper atmosphere even more puzzling. Because if the planet is still generating heat, even at a low level, then why is the ionosphere, the region most directly exposed to both solar radiation and energetic particles, losing temperature over time instead of maintaining a balance? One possibility is that the mechanisms that transport energy from the interior to the upper atmosphere are not as efficient as we thought. That heat is being trapped deeper within the planet or redistributed in ways that prevent it from reaching the ionosphere. Another possibility is that the rate at which energy is being lost to space has increased, perhaps influenced by the planet's unusual magnetic field, which could be channeling charged particles in ways that enhance cooling. And then there is the role of the solar wind, the stream of charged particles flowing outward from the sun, interacting with Uranus's tilted and offset magnetic field in ways that are far more complex than what we see at Earth, potentially altering how energy is deposited and removed from the system. But here's the problem, and this is where it becomes genuinely uncomfortable. None of these explanations fully account for what we are seeing. They are possibilities, not solutions. Pieces of a puzzle that still doesn't quite fit together. And the more precise the data becomes, the harder it is to ignore the gaps in our understanding, because now we are not dealing with vague estimates or uncertain measurements. We are dealing with a clear trend that demands an explanation. So what you end up with is a planet that should already be cold, becoming colder still, an atmosphere that is quietly losing energy over decades, and a set of models that cannot fully explain why. And if you step back and look at that situation, it tells you something important, something that goes beyond Uranus itself. It tells you that even in a system as familiar as our own solar system, there are processes at work that we have not yet fully grasped. Patterns that emerge only when we observe over long periods of time, and behaviors that challenge the assumptions we didn't even realize we were making. And that, in a way, is the real discovery here. Not just that Uranus is cooling, but that it is doing so in a way that forces us to confront how little we truly understand about the flow of energy in planetary atmospheres, especially in worlds that refuse to behave like the ones we used to build our theories around. There is a moment in science that doesn't come from discovering something entirely new, but from realizing that what you thought was disorder is actually hiding a kind of structure you weren't prepared to recognize. And that is exactly what happens when we look at the auroras of Uranus through the eyes of the James Webb Space Telescope. Because up to this point, you could still explain everything we've seen as complexity layered on top of uncertainty. A planet too distant, too poorly observed, too unusual for our models to handle cleanly. But the moment those auroral patterns emerge, that explanation starts to break down in a very precise way. Webb detected two bright bands of infrared emission positioned near the magnetic poles, arcs of light produced by charged particles, accelerating along magnetic field lines and colliding with the upper atmosphere, releasing energy in a form we can measure. In principle, there is nothing unfamiliar about that mechanism. It is the same basic physics that creates the northern lights on Earth, the same process that drives the intense auroras of Jupiter. But what makes Uranus different is not the existence of auroras. It is the environment in which they form. The magnetic field guiding those particles is tilted, offset, and constantly shifting relative to the planet's rotation, which should make the resulting patterns unstable, irregular, difficult to predict. And yet, the observations tell a different story. Those bright auroral bands are not scattered randomly across the planet. They appear in locations that correspond to the expected geometry of the magnetic field, suggesting that even in a system that looks chaotic from the outside, there are underlying constraints shaping how energy is distributed. This is not randomness, it is organization. But organization that emerges from a configuration we don't fully understand. Then comes the detail that complicates everything further. because between those two bright regions, Webb revealed a darker zone, a gap where the infrared emission drops sharply and the density of charged particles decreases, creating what is effectively a corridor of reduced activity. This is not just an absence of light. It is a region where the usual processes that generate auroras are being suppressed or redirected. And that immediately raises a question that cannot be ignored. What is controlling the flow of energy so precisely that entire monodic of the ionosphere can be deprived of it? There is a clue, but it doesn't come from Uranus itself. On Jupiter, similar dark regions have been observed where magnetic field lines extend outward into space rather than looping back into the atmosphere, allowing charged particles to escape instead of depositing their energy locally. The presence of a comparable feature on Uranus suggests that its magnetic field, despite its distortion, is not acting randomly. It is carving pathways, defining regions where particles are funneled inward and regions where they are carried away, effectively sculpting the ionosphere into zones of brightness and zones of relative emptiness. What makes this even more intriguing is that these patterns are not fixed in place, because the magnetic field of Uranus is not aligned with its rotation. It does not simply spin with the planet in a stable configuration. It wobbles, precesses, and shifts, meaning that the auroral structures move over time, sweeping across the atmosphere in patterns that evolve as the planet turns. This creates a dynamic system where structure exists, but that structure is constantly changing, a balance between stability and motion that is far more complex than anything we see on Earth. At this point, the interpretation becomes unavoidable. If the auroras were completely chaotic, we could attribute them to the complexity of the system and leave it at that. If they were perfectly orderly, we could rely on our existing models to explain them. But what we see instead is something in between, a system where there is clear structure, clear organization, but governed by rules that do not fully align with the frameworks we have built from studying other planets. And that is where the real significance lies, because these auroral patterns are not just visual phenomena. They are indicators, traces of how energy flows through the interaction between the solar wind, the magnetic field, and the upper atmosphere. They show us where particles are being guided, where they are being lost, and how the geometry of the magnetic field influences the distribution of energy on a global scale. So instead of simplifying Uranus, these observations make it more demanding, because they reveal a system that is neither random nor fully understood, a system where order emerges from distortion, where structure exists within apparent chaos, and where every new detail forces us to reconsider how magnetic fields and atmospheres interact on worlds that do not behave like the ones we are used to studying. There is a subtle shift that happens when a single planet stops being just a destination of curiosity and becomes something far more important, a reference point, a kind of template that quietly influences how we interpret worlds we cannot directly touch. And that is exactly what is happening with Uranus right now. Because the moment you step back from the details, from the cooling ionosphere, the strange auroras, the distorted magnetic field, you begin to realize that this is not just a story about one distant, overlooked planet. It is about a category of worlds that may be among the most common in the entire galaxy. When astronomers look beyond our solar system and discover planets orbiting other stars, they rarely find exact copies of Earth or Jupiter, but they very often find something in between, worlds 2 to 4 times the size of Earth, with thick atmospheres, substantial volatile content, and internal structures that resemble what we classify as ice giants. In other words, planets that are much closer in nature to Uranus and Neptune than to the gas giants we tend to focus on. So when we struggle to understand Uranus, we are not just missing details about a single object. We are potentially misinterpreting thousands of exoplanets whose only clues come from faint signals of light filtered through their atmospheres. And this is where the observations from the James Webb Space Telescope begin to carry a weight that goes far beyond the outer solar system. Because what Webb has revealed is not just complexity, but inconsistency with the models we have been using to describe how planetary atmospheres behave. Those models, often simplified into one-dimensional frameworks, assume relatively smooth variations of temperature, density, and composition with altitude, guided by well-understood physical processes like radiative balance and chemical equilibrium. They work reasonably well for planets that behave in predictable ways, but Uranus is showing us a system where those assumptions begin to break down. The data indicates that temperature peaks and ion density peaks do not align as expected. The charged particles are distributed differently than our models predict, and that the overall densities in the ionosphere are lower than anticipated. These are not minor discrepancies. They are structural mismatches, suggesting that there are additional processes at work, processes that may involve complex interactions between the solar wind, the planet's unusual magnetic field, and atmospheric dynamics that redistribute energy horizontally as well as vertically. In other words, the system is not one-dimensional. It is deeply three-dimensional and time-dependent, and our models have not fully caught up to that reality. Now consider what happens when we take those same simplified models and apply them to exoplanets, worlds that we cannot observe in detail, where we rely on interpreting small changes in starlight to infer atmospheric properties. If our models are missing key processes, if they fail to capture how energy actually moves through a system like Uranus, then the conclusions we draw about those distant worlds may be incomplete or even misleading. We might be estimating temperatures incorrectly, misjudging atmospheric composition, or misunderstanding how those planets evolve over time, all because our reference framework is built on assumptions that do not hold in more complex environments. And then there is another layer to this, one that makes the problem even more interesting. Uranus is not just complex, it is accessible in a way that exoplanets are not. It is close enough that we can observe it repeatedly, measure it over time, compare new data with decades of previous observations, and eventually send spacecraft to study it directly. That means it serves as a kind of testing ground, a place where we can refine our understanding, challenge our models, and develop more accurate frameworks that can then be applied to the broader population of planets beyond our solar system. So what Webb has really done is expose a gap, not just in our knowledge of Uranus, but in the tools we use to interpret planetary atmospheres in general. It has shown us that even in a relatively nearby system, where we have decades of data and a strong theoretical foundation, there are still behaviors we cannot fully explain, patterns that do not fit neatly into our existing models. And if that is true here, where we can observe in detail, then it is almost certainly true for the countless worlds we can only glimpse from afar, which means the problem is not just that Uranus is strange. It is that Uranus is revealing the limits of our assumptions, forcing us to rethink how we model planetary systems, how we interpret incomplete data, and how we bridge the gap between what we can observe directly and what we can only infer. It is no longer just a distant tilted planet drifting quietly at the edge of the solar system. It has become a critical piece of a much larger puzzle, one that extends far beyond our own cosmic neighborhood and into the countless planetary systems scattered across the galaxy. If you follow the story all the way to this point, there is a temptation to think that we are close to an answer, that with enough data, enough observations, enough clever models, we might finally close the gap and explain everything that Uranus has been quietly revealing. But that instinct is misleading, because what we are actually approaching is not a conclusion, but a boundary, the edge of what remote observation can realistically give us. And beyond that edge, there is only one way forward, because everything we've learned so far, every temperature profile, every auroral structure, every hint of cooling in the upper atmosphere comes from interpreting light, from decoding signals that have traveled billions of kilometers before reaching our instruments. And while that has taken us remarkably far, it also introduces a kind of distance that cannot be eliminated. You can infer, you can model, you can compare patterns across time, but you cannot directly test the environment you are studying. And that limitation becomes more significant the more complex the system is. And Uranus is not just complex, it is layered, dynamic, and in many ways internally hidden from anything that remains outside of it. Take the magnetic field. For example, the same distorted, off-center structure that shapes the ionosphere and drives those shifting auroras. From afar, we can reconstruct its geometry indirectly, watching how charged particles move, how emissions appear and disappear. But that is still a reconstruction, a shadow of the real thing. To truly understand it, you would need to move through it, to measure its strength and direction point by point, to see how it evolves, not just over hours, but over weeks and months as the planet rotates and interacts with the solar wind. That kind of knowledge cannot be extracted from a distance. It has to be experienced from within the system itself. And the same is true for the atmosphere. Right now, we describe it in layers. We assign temperatures, densities, compositions based on spectral data. But those are still interpretations, built on assumptions about how gases behave under extreme pressure and temperature. To resolve those assumptions, you would need to descend to pass through the clouds, to directly measure the ratios of hydrogen, helium, methane, and heavier elements. To understand not just what is there, but how it is distributed, how it changes with depth, how it connects to the planet's formation history. That is not something a telescope can ever do, no matter how advanced it becomes. This is why the idea of a dedicated mission is not just an extension of what we are already doing. It is a fundamentally different step. An orbiter would transform Uranus from a distant object into an active environment, something we can monitor continuously, something we can map in full three-dimensional detail over time, following the motion of charged particles, tracking the shifting boundaries of the magnetosphere, observing how auroras evolve not as isolated events, but as part of a larger system that breathes and changes. And alongside it, a probe descending into the atmosphere would provide a kind of ground truth, a direct measurement that anchors everything else, turning models into testable hypotheses rather than educated guesses. But there is another dimension to this that is easy to overlook, and that is the system surrounding Uranus, the collection of moons that orbit it, each one a record of past events written in geological form. Among them, Miranda stands out not because we understand it, but because we don't. Its surface appearing fractured, mismatched, as if it has been broken and reassembled, with enormous cliffs and irregular terrain that suggests a history far more violent or complex than a small moon should have experienced. And yet, the only close images we have come from Voyager 2, captured in a brief flyby that left more questions than answers. A long-term mission would change that perspective entirely, allowing us to revisit these worlds, to map them in detail, to understand how they formed, how they evolved, and how they interact with the planet's magnetic and gravitational environment. It would turn isolated snapshots into a coherent narrative, linking the structure of the moons to the history of Uranus itself, revealing whether the planet's strange tilt, its internal dynamics, and its surrounding system are all connected pieces of a single larger event. And yet, all of this remains in the future. Not in the sense of uncertainty, but in the sense of time. Even under the most optimistic scenarios, such a mission would take years to launch and more than a decade to arrive, meaning that for now, Uranus remains just beyond our reach, close enough to study, but far enough to resist direct exploration. So what we are left with is a kind of asymmetry, a situation where our questions have advanced faster than our ability to answer them, where each new observation sharpens the problem without resolving it. That is the state of the story. Not unfinished in a simple way, but open in a way that demands continuation, because the most important pieces are no longer theoretical, they are physical, waiting in an environment we have not yet entered, part of a system we have only observed from the outside. And until we cross that distance, until we move from interpreting signals to directly measuring reality, Uranus will remain what it has quietly become through all of this: not a solved problem, not a forgotten planet, but a frontier that we have only just begun to approach.